All right, let's get started. Thanks for joining everybody. Today, we're going to go over Comet. It's a paper about fine-grained computation and communication overlapping for a mixture of experts. This is my favorite one in a while, I think, so I'm excited to talk about it. I have some questions of my own about it that I'm curious to pose to the group and see if anybody has any thoughts. Yeah, first, I'll just do a quick couple minutes on some background needed so that anybody who has not been doing any MOE related work or kernel authoring, we'll still be able to get something out of this, and we'll be able to have a shared vocabulary for this. Um, Not a deep dive though. This is just very high level overview. So on the MOE side, the paper is dealing specifically with like something called token choice routing in MOEs. Um, as a background, just for an MOE layer, how it differences from the difference from like a regular transformer block and like a dense model is instead of attention going into just a regular FFN, the attention outputs, the output activations, go through something called like a gating network or a routing layer, which you see here in green. And that's usually just a linear projection to the expert dimension, meaning that you'll get some score for each token for each expert, right? Then you can pass this through something like a softmax or a sigmoid. There's different ways of doing it. And then from those scores that you can interpret as probabilities, you could say, I want to pick the top k. And usually k is like say 1 or 2 or something like that. And then for each token, it will go through the computation for the assigned expert, as you can see here. Like say this token goes through expert 2 and then this expert n minus 1. And so now you have two tokens, two outputs that need to be reduced afterwards, which you can see here. And you get like an aggregated update of the token's position in vector space based on two different sets of parameters. So basically the motivation for using this type of architecture is twofold. One is that it allows you to expand your parameter count, as you can see here. Instead of like one FFN, we have n FFNs. So you can greatly expand your parameter count while on a fixed compute budget, meaning that these experts, as you noticed, are sparsely activated. We're not unconditionally going through all the parameters at each step. So you can expand your parameter count, which is great for things like knowledge integration and emergent behaviors and all kinds of researchy things, but keep the same number of like flops for like a comparable dense model with fewer parameters. And what this results in is things like your experiments have shown that you can hit like the same training loss with fewer steps, you can hit the same eval metrics with fewer steps, and so on. So it's a very compelling paradigm, basically. So that's why people use it. And that's how token choice routing works. And this is important for the paper today. Other piece of background is the actual kind of compute primitives used in these MOE layers. So how do they efficiently implement token choice routing with a variable number of tokens assigned to each expert? Which, by the way, that in itself, there's a lot of nuance and detail. We could get into all the problems that causes, but it's not really the focus today. But I do want to mention that if you're curious, go read more about that. But anyways, as far as how to actually implement this, naively you could just launch a separate matmul, like in a loop, like for each token group, for each expert, just launch a separate matmul. But then you have like the CPU overhead of all the kernel launches. You have smaller gems, smaller kernels. It's just less efficient. Then you could do something like a batched MM and just pad the token group so that all these squares here we're looking at, right, or these input activations are all the same size. They're static shapes, and you could do like a BMM. But then you're wasting a bunch of compute on like a bunch of padding, and extra memory, and compute. So that's not optimal. So there's this different compute primitive called group gem, and it basically allows like a 2D. So this diagram isn't the best. I actually have a different one, but I only made it for like internal stuff at work, so I can't share it here. But basically, the input activations are a 2D tensor that have been flattened. So you have the row dimension is your token dimension, which will be like batch size times sequence length times top k, right? Because each token is going to top k experts. And then n is just your token dimension, basically your embedding dimension. But the expert weights pictured here as multiple identical 2D tensors. are typically a 3D tensor. So you can picture like stacking these tensors on top of each other. So it's like a 2D by 3D gem where you give, as part of your parameters, you give this input x tensor, this 3D input weight tensor, and then you also provide a list of offsets, which are like delineating the end index of each token group. So you say the end of expert one's token group is at index 4, and then the next one is at 5, and then the next one is at 7, and so on. So that way, the group gem implementation understands how to do the matmul, which rows to do the gem with for each expert weights. And then as you can see here, you get these outputs, right? And then you just conceptually they're just stacked, and you get like a 2D output, right? So that's the gem, the compute primitive they're talking about in the paper today. Brief pause. Does that make sense to everybody? Are we good on this? Okay, cool. Next thing is a bit more complicated. I'm just going to pop open the actual source here. It's about the comms pattern in MOEs. So specifically in the paper they discuss expert parallelism and tensor parallelism. Um, Basically, where is it? Expert parallelism. So um, the paper discusses how to fuse kernels for comms and compute overlap. So it's important to understand what are the comms and what are the compute that we're trying to overlap. So um, it references all-to-alls and all-gathers and stuff without any explanation. So here's the explanation. So basically, if we just look at one host here, one device on one host, this is one. This is with TP and EP. Basically, so expert parallel and tensor parallel. Basically, this orange is the shared expert, which is also another thing in MOEs. You might have like one shared expert that all the tokens unconditionally go through. The idea being that that will give some kind of baseline knowledge that doesn't need to be relearned across all the other experts for some shared representation. Whereas the other experts can then focus on just kind of more specialized, updates basically. And so how this works basically is, so this is, okay, this is not a generic implementation, but it's the best diagram I could find. I'll go over what this is doing, but just to be clear, like these specific like index shuffling gather mul, these are like implementation specific details for this blog, but what this is doing is computing the routing scores, like I talked about, the routing layer, right? Compute scores, token affinity scores for each expert. Index shuffling is shuffling the actual metadata, I believe. So I think it says down here, actually, I can just double check myself. I believe it's just like metadata shuffling. Let me see. I don't want to lie to everybody right here. Shuffling and sorting of indices. So yeah, metadata. It's just shuffling token indices and not the actual data itself. And to be clear, what this means is basically we're going to need the tokens in the same contiguous order as the experts when we perform the gem. They can't just be in some random order, right? So if your local tokens have been assigned to expert like 0, 3, 4, 1, and 2, you need to sort them such that they're in the same order as the experts in the 3D tensor so that you can do the group gem. They can't just be like random. So that they call it shuffling. The gather mul is the same sort of thing, but I believe it's actually moving the data now that shovels the tokens themselves based on the sorted indices and then scales them. So based on the sorted indices that we just got in index shuffling, we then can move the actual tokens, and then it does scaling for low precision, which is just like another optimization, which we won't get into. But the main stuff I wanted to focus on in this diagram was these comms. So these all-to-all comms, what they're doing now is saying for every device, every token that is assigned to an expert that lives on a different device, because we're using expert parallelism, right? So the experts live on different devices. We are going to send those tokens, dispatch them in a step called all-to-all dispatch. We're going to dispatch them to the other devices where their assigned expert lives. And every device is going to do this at the same time. And so it's an all-to-all communication because we're potentially sending, we're doing comms across from every device to every device. And what we should get is all the tokens that need to run on our local device, right? And they have two all-to-alls here. Apparently, one is for metadata exchange first, and then they do the actual data transfer in a second all-to-all. They say it here. They say exchange on device metadata tensor about number of tokens routed to each expert, and then they exchange the actual data. But I don't know. The implementations I've seen, there's just one all-to-all right here. So this is, I don't know, an extra optimization or something. But anyways, then we do combined shuffling. So we permute the tokens. Now that we have other tokens, they actually do the permutation to get the tokens in the order for the gem. So reshuffles receive tokens from rank first order. Rank first meaning that's the order that they came in via data transfer. It does data transfer in rank order. And then now they need to be in expert order for the actual gem. Okay. And then we can finally now do our group gems that we talked about, go through our experts that are assigned on the device. Very cool. And then now we basically do an all-to-all combine, which is sending back, like basically each device in this in this form of parallelism, each device is responsible for a subset of the tokens, and we need the aggregated updates that token went through when we dispatched it to various devices, right? We went to our router and we say, okay, this token goes to top K, so like 2 experts. We send it to those 2 devices, say, and then we get the outputs back, and we need to aggregate them. This is all-to-all combined. And then this all reduce here is for TP, basically. But that's kind of the high level flow. I mean, this is like pretty complicated as you can see, but just the main ideas we need to take from this are before the group gems, there's all-to-all comms if we're using expert parallelism. There's all gather comms if we're using TP with sequence parallel, which is often used. And then afterwards, there's all-to-all comms, all-to-all or combined comms if we're using expert parallel, and then also reduce scatter if we're using TP with sequence parallel. Okay, so that's the all-to-all. Those are the comms referenced in the paper that you see, and that's why they are relevant and why you'll notice here. The key thing to notice: these are strictly sequentially dependent. You see how these are not overlapping, these gems and these all-to-alls? They are strictly like this is a hard data dependency. We have to wait for the data to arrive before we can begin to do the gem, right? Okay, and that's what the paper is going to try to address. They're saying, can we overlap this somehow and do this in some more sophisticated or intelligent way? Does that make sense, at least at a high level? The main takeaways about all-to-alls before and after, all gather and reduce scatter before and after, and the strict sequential dependencies between them? I'll pause if anybody has any questions.
Yeah, just to confirm. So the group gem is just waiting for all the tokens because it can then pad and then multiply with the expert weights internally, but it can also do that in parallel, right? Like it doesn't really need all the tokens from all the experts for doing it, right? Like the weights are separate for all the tokens and experts, isn't it?
Yeah, so you're basically starting to think ahead for what the paper is going to, like the insights that they have. But if you just like so if you just use the raw primitives, like the alt-all
Mm-hmm.
single from PyTorch, like it's like dis.alt-all single, this is like a blocking multi-device operation, and the group gem will wait on it. Like
Mm.
it's
Oh, okay.
so like technically yes, a certain expert's token, like expert zero, its tokens might already all be there, but it will still be
Mm.
waiting for this blocking collective op to finish.
Oh, interesting. So,
Mhm.
like, does the paper come up with a new collective or a communication operator for this, or
Kind of.
do they go? Okay,
Yeah, yeah.
interesting.
We'll see. You could call it a new collective. It's a fused compute and comms kernel that does not just quote unquote naively call the provided standalone primitives here, and we'll see how they allow kind of more granular overlapping here as dependencies become available.
Oh, interesting. So
Hmm.
it's like, okay, so it's interesting. Okay, that I'll wait for when we get there. But yeah, this is cool. Yeah, thanks.
Yes. Cool. All right. Anybody else? Any other? Okay. Cool. So back to the slides then. We're now ready to jump into the actual paper, which we started kind of alluding to a bit just now. So first for just the motivation for the paper and the limitations of the prior work. So on the right here, basically you can see this diagram from the paper where the authors did some experiments with some prominent open source MOEs, and they found that up to 47% of the forward pass execution time is used by exposed MOE comms, the alt-alls and all gather, reduce scatters, etc. that we talked about. Because especially, okay, so TP on its own, as we know, is like a comms heavy form of parallelism, and then MOEs, that's like, doubly so, like alt-all. I mean, just in the name, it's there's a lot of comms going on there. So yeah, there's a lot of room for optimization here. Basically, 47%. That's crazy. So, what methods have been tried for this? So basically, a couple like the main one they mention is just a form of pipelining with kind of more coarse-grained decomposition, which we can see a diagram on the bottom here, where basically the data coming in is somehow logically grouped into chunks, and in this example, it's two chunks, and it kicks off and it does runs those comms kernels in one CUDA stream, and then in another CUDA stream, it runs the computation kernels, and just after the first chunk of data finishes arriving, it starts running the compute, and so we have two, and then our outgoing comms. So these are like this top thing would be the incoming comms, do the compute, and then outgoing comms, right? We talked about like all group gems, and then all combine or reduce scatter. This is like a very kind of simplified kind of version of what that might look like and the kind of overlap you might see. And it's important to note this is like the best case scenario where you actually do have overlap. And the problems they point out is that this does not always happen basically. Like this is non-deterministic in the implementation. So when you just launch stuff on streams like this, they might be misaligned and you don't have ideal overlap. The dynamic nature of the workload itself means that comms or compute kernels might take more or less time depending on how many tokens were assigned to the experts on this device, right? So that's non-deterministic. And then just in itself, the act of decomposing your gems are going to be smaller, which means lower tensor core utilization. So that's another downside of that approach. And yeah, that's kind of the issue there, like irregular and non-deterministic overlap and some underutilization problems. So there's more problems though beyond just that. So if we think about, is there a smarter way to do that? Oh, I was going to say one more thing. Sorry, is that the other problem is that there's unavoidable idle time at the start and finish for the first receiving ops and then the last sending ops. And depending on the chunk size, that will kind of determine how big those unavoidable bubbles are. And if you want to do finer grained overlapping, it kind of becomes more complex. It's not straightforward for a couple of reasons. One is that there's complex data dependencies between between things here. So, for example, these gem operations occurring for the experts, and then the input, the data transfer coming to like write those inputs to the buffer where we're going to read from for the gems. The dependencies are complicated in the sense that like a single tile, if we look at the purple here, the tile, which is like a unit of compute for computing gems, like a 128 by 128 tile, say, um, it will depend on both local data that's already there from our input activations, as well as remote data that needs to be sent. Because remember, we're doing the all-to-all for the tokens. So In this example, you can see this tile will depend on both token A, which is already locally available, and then token B, which is on a remote device. And so it's not so straightforward to just to start doing more granular operations. And they also call out a granularity mismatch in the sense that the fundamental kind of unit of compute or like level of granularity, in gems is the tile. It's like like say like a 128 by 128 tile. I mean, this is like like auto tuned a lot of times, but just as like an example, say it's 128 by 128. The fundamental unit of data transfer conceptually, right? I mean, obviously we're just sending bytes, but the it is the token here, right? Because each device is going to dispatch the tokens that need to go through experts on other devices, and just fundamentally, you can see this purple tile, if it's 128 by 128, it's going to have to wait until 128 tokens have all been written and are present, and those writes are visible to it. And even though it doesn't need any of this data on the right here, it only needs the data in the tile, right? Like this chunk of columns. And if you think about this effect is actually much more exaggerated in real life because in this example, the tile is half of the entire token dimension, but in real life, it's not in real life. It's much smaller. It's like, I don't know, 10 or 20 times smaller. But so yeah, you have like a tiny little tile here that wants to compute, and it's like that 128 rows. It only needs 128 columns, but instead it's gonna have to wait for like 16,384 columns times 128 rows to be written. And that's all. A lot of that is gonna be transferred over the network, whether even like over NVLink. Like this is a substantial like stalling for actually scheduling this. So yeah, that's what this mismatch in granularity is a problem. So basically, they're kind of, observing and saying it would be nice if the way we did our data transfer, or just more generally, if the way we did our dependencies, um, was done in such a way that we were writing only what we need to kick off the first tiles of compute immediately while other data transfer is still going on. So like write this purple tile and then other data transfer can still be ongoing, but at least now we're starting to kick off getting the computation flowing and we're having overlap this whole time. And the same thing, we've been talking a lot about dependency between the data transfer and then the gem, but it also works the other way in the subsequent layer, right? Because the FFN, the expert is an FFN where it's usually like, just say like two linear separated by a activation function, except with, it's a group gem, there's multiple experts, so it'll just be like 2 by dim by hidden dim instead of just like dim by hidden dim. Here, the dependency is the gem, and then the consumer that is like dependent on that is the comms, right? And so until that gem finishes writing things, and it's going to be writing like output tiles, these rows can't be transferred, so to speak. So yeah, does that kind of mismatch make sense to everybody? Before I move on, okay, cool. The other problem, this is the last problem before we get into the solution, is basically dynamic resource requirements for comms versus compute workloads. Basically, they did this in DeepSeek v3 as well, where they dynamically adjust the amount of resources. I think they just adjust the number of SMs carved out for comms on the fly, like during training. But they do it differently in this paper. And basically, they don't actually. If we just look on the right, this is something where they didn't elaborate, and I'm just speculating. So they say. The variable number of tokens per expert imposes like differing communication and computation demands on different GPUs. Achieving seamless overlap between computation and communication thus requires dynamically adjusting the allocation of GPU resources to different workloads, which is hard to be realized through wrapping workloads into separate kernels. Um, yeah, so I think what they're saying here with the variability imposing different communication and computation demands is basically like if one GPU has, 10 tokens for its various experts that live on it, and another GPU has 50. It's not like I don't think I might be wrong, but it doesn't seem, it's not like a linear difference where we can just say like, okay, well this is like, we'll just assign, um, 5 times more, um, you know, comms and compute resources for, or I guess I should say, never mind. What I said didn't make sense. What I said didn't make sense. What I'm trying to say is this summary that I wrote here, which is basically, and this is by the way, this is my speculation. So I would like people's thoughts on if this actually makes sense. I was just thinking, why the ratio, because what they're talking about is the ratio of comms to compute, right? How much when we dispatch this kernel, how much SM resources do we need to devote to computation versus communication to ensure that there's not idle time for either. That like roughly, they roughly are the are taking the same amount of time, and there's no big bubbles as we like the compute say is going much faster than the comms, and so there's like big gaps between our tiles of computation, like they can't be scheduled because it's waiting on data transfer, or vice versa. And I was thinking that basically, um, the flops required to compute a gem, the multiplicative factor when you add a new token, for every new token, it's going to be, you grow your number of flops required by 2 by n by k. Whereas for that token, the data transfer only grows by token dim, which is like a different factor and like a smaller one. So, basically, and token dim, I think really is just n, if I'm not tripping, or is it k in this case? We're projecting. It depends on the gem. I'll just put dim. Um, but anyways, the number of bytes we're transferring grows by this factor, but the number of flops grows by this factor, and so it's like a nonlinear relationship where, um, if we increase the number of tokens that are going to need to be computed on a given device by 10, suddenly the optimal ratio of compute versus comms resources has changed. Um, does that make sense? I mean, is there something that maybe that doesn't make sense about what I said?
Okay, so just to confirm this, like each expert, depending on how many tokens it has routed, it might have a different communication load and the computation load. That's what we are saying, right? Like the
Yeah,
load is not fairly balanced across all GPU devices.
exactly.
Okay.
Yeah. So basically, what I'm saying is, if for like there's no, say we devote, like just naively, say we have like two SMs dedicated to compute and then two SMs dedicated to comms, and that
Mm.
works well for 10 tokens that we need to process on this device. If that grows to 20 tokens, that same ratio is no longer optimal, basically.
Mm.
And I was trying to
Interesting.
think about why. And this is what I came up with, is basically the compute requirements would scale differently than the data transfer requirements, just in terms of, you know, processing needed, basically. That's my speculation. If
Okay.
anybody has a different interpretation, I'd love to hear it.
Well, that makes sense. Like, can I ask, like, this allocation of what SM will do communication and what SM will do, or which SM will do computation, like, that decision is made at which level of abstraction in GPUs? Like, do we even control that?
Yeah, well, we can control it. That's just like by default we do not, but you can. There's like techniques like SM carve out where you just like explicitly carve out SMs like a static number for comms, and there's other techniques like what's the word? Well, what they do in this paper is basically oh, spoiler alert, basically they pre-compile, they do basically a bunch of analysis and pre-compile kernels with different SM ratios for comms versus compute, and then dispatch dynamically on runtime based on the problem size and the parallelism configuration. Um, so
Oh,
so it is controllable, basically is what I'm saying.
okay, that's
Yeah,
nice.
and DeepSeek does it as
That's good.
well. Like during training, they like monitor somehow, I can't remember exactly how, but and then they adjust the ratio of the number of SMs dedicated to comms, like during training, to keep overlap optimal or something like that. I haven't read DeepSeek v3 in a while, but I remember they mentioned something like that.
Okay. I'm guessing this
Oh,
goes against the whole persistent kernel theme. Like you won't be able to have that. Okay. Okay. That's a topic for another discussion. Okay. Thanks. I
well,
think someone else was also talking.
yeah. Sorry, it's me, Zippy. Um, I feel like you wouldn't necessarily know beforehand for like some rank how many tokens are going to be sent to you
Hmm.
if it's extra parallel, right? So then it's not. It wouldn't necessarily be optimal always, right?
Um, yes, but well, no, because like you don't know ahead of time, but when it comes time to actually dispatch the kernel, um, you will know the problem size. You won't know ahead of time, but like when you actually do the kernel dispatch, you will.
Okay.
Yeah, we'll see later in
So
the
does it
in
like
the
send?
paper.
So does it send metadata? Is there like a like I'm sending you 3 tokens, from this, expert parallel rank,
Yeah, that
and
was kind
this
of in
other
this here the
index shuffling.
yeah, the
Yes.
shuffling where they pass back and forth the metadata. It said something like, where is it? That was
That does
it.
make more sense. Then.
Yeah. No, it wasn't either of those. I'm curious as well. It was one of these. I remember just reading it. Gather mole.
You mean sending metadata before the actual like data?
Yeah. Oh, you know where it was? It was I remember here. It was alt. It was the first all to all
Yeah.
here.
Yeah.
They
You're doing two
exchange.
all to all, and the
mm,
first one is for metadata.
Yeah, yeah.
Yeah.
They exchange
Okay.
on-device tensor metadata about the number of tokens routed to each expert before they actually
Uh,
exchange the data, and then they can do
so
the
I feel like
gems.
the index shuffling would be reordering, like the actual data, so that it, like
Yeah,
preparing to send chunks.
yeah, it's weird. They just say index shuffling, they sort indices only, and then in gather mole is where it sounded like they actually do movement of the token data and then scaling for FPA, I believe. Um, the shuffles, to yeah, because index shuffling handles shuffling based on indices. Um,
Oh, okay.
and then this says shuffles tokens based on the sorted indices and scales them. I don't know why they break it up
So there's
into,
probably some like select in the.
yeah, it's like an implementation thing, I think. But yeah,
Oh, that's maybe the gather mall is the select. It's like a scale and a select.
yeah. Yeah, I think so. Okay, where were we? Okay, yeah, here we are. Okay, so we were on this slide, and now we're going to finally take a look at how they are proposing to address these problems. Which again were like the granularity mismatch, the irregular non-deterministic overlapping, and the dynamic workload resource requirements. So how do they solve this? This is a high-level like design of their solution. It will make a lot more sense on the subsequent slide. This one is kind of unclear to me personally. Basically, what this the takeaways from this diagram are they structure the MOE as a two-stage or two different pipelines, like which are I view as like different stages. They call them layers. I guess they are layers. It's like the first layer in the FFN, the second layer in the FFN, or like the grouped experts. Really, I keep saying FFN, but um, yeah, I don't know. I think of them as like stages, like the first stage of the MOE and the second stage, because they're separate producer consumer pipelines. Where in the first one, our producer is the comms, consumer is the computation of those comms, and then we do our activation function. Then we have our second group gem, and then our comms, which is the producer, and then our comms, which are the uh, consumer. But this is a little misleading. This outgoing comms thing actually has a top K reduction first before the comms, which is important for reasons that we'll see. But basically, each of these producer-consumer pipelines have a shared buffer that they use to facilitate kind of smart rescheduling of the tiling of the computation, right? Because by default, I don't know what the default algorithm is for scheduling tiles in a gem, but they basically implemented their own custom tile scheduling that does something like this, where you know what, let's just go to the next slide because this decomposition or rescheduling will make a lot more sense with some annotations, which this provides. So basically, what this is saying is, see how this blue and uh, beige, I guess, are local data and then remote data. What it's saying in this previous decompose and reschedule thing on the left here, it's saying that rather than just naively saying, okay, expert zero, let's compute you and all the input tokens that are assigned to you. Oh, but we have to stall and wait because we're dependent on remote data being transferred in for those tokens. Basically, it reorders the computation and says, let's do a different group gem that's not specific to whatever, expert zero and expert one, but rather specific to the tokens that are locally available. So it just so happens that for the local tokens we had on the device when we did our routing, these blue ones are the ones that were assigned to experts, or sorry, I missaid that. For the experts that happen to live locally on our device, which are 0, 1, and 2, these are the tokens that happen to already be on our device as well. And so it will structure the group gem and say, okay, expert zero tokens, which are the first three, and then this last one is for expert one. So we do a group gem with these four tokens and expert zero and one, where our offsets would be like indexes 0 through 2, and then 3. Okay, so that's like a first group gem, but it's just implemented differently to essentially specifically prioritize data that's already locally available, rather than just the kind of like default implementation that has no awareness of this, right? Then it will move on to the second gem, where we again try to prioritize the locally available tokens, and basically we postpone usage of any remote data until as long as possible. And they do this by quote unquote sorting the tokens by source rank. And yeah, that's what it states. To me, actually, that explanation is not super intuitive, just because maybe this is a noob question, but I didn't see why. Like, yeah, if like if you sort tokens by source rank, you can just say, okay, my local rank, yeah, that will be at the beginning of the list, and everything else will come after in some like circular list, basically. But then how do you know? For like there could be different network latency, especially if this is multi-host, where some of these remote ranks will be on devices on your host connected by NVLink, which is much faster than some devices which are going to be connected via InfiniBand, which is like lower bandwidth, higher latency. So doesn't that kind of just ignore that? And you might be waiting on InfiniBand data rather than something you can get over NVLink much faster down here. Does anybody have any thoughts on what it means they say sorted by source rank? Like, does what I say make sense about the different network latency?
Um, why are you assuming that the source rank of a GPU, which is internode, is lower than the source rank of internode? Like,
Can you say that again? I didn't follow.
like the source rank for something which is on another node. Like, why are we saying that its source rank might be lower than the source rank of a GPU on the same node?
I think they're
Because
saying the opposite. I think basically what they're saying is like, I think sorting is kind of a shitty term, but like they're basically saying like, if I'm whatever rank 2, then I will prioritize everything on rank 2, then 3, then 4, then 5, then 6, then 7, and then 0, and then 1. I assume they don't actually give any examples, which is like really annoying, but that way we know for sure that prioritizing rank 2, our rank, the data is local. and we sort that way. And then the others are all remote. And I think my point is that I feel like by treating all remote ranks as equal, that's like non-optimal, right? Because shouldn't you sort by first local, then NVLink, intranode, then InfiniBand, like other node, like external node ranks, right?
Yeah, that makes sense to me. Yeah, I was just thinking that maybe they had some clever ranking or device labeling method which
Yeah,
made it so that the local ones had like they were closer in rank or something like that.
yeah.
Yeah.
I was thinking that would be handled on like the ML framework layer, like PyTorch, because that's to my like at least the way
Mm-hmm.
I've seen ranks, like that's what is assigning and like your device mesh, you have like the ranks based on your world size, but it doesn't, to my knowledge, do any kind of smart numbering based on network topology basically. But
Hmm.
and and yeah, and it wouldn't make sense anyways because the rank is global. So from like one device's
Hmm.
perspective, you would have different. I don't know. Maybe I don't know. Maybe I haven't thought about it enough, and like it would be the case if you sort. Then from any device's perspective, the nearest ranks would be. Maybe that does make sense. From any device's perspective, if you sort the ranks, the nearest ranks, like sequentially in sorted order, would be like on the same host, and then the ones farther away would be on different hosts. Or maybe it's at
Yeah,
least
like
like
yeah, that's definitely possible, and that sort of works with the circular list sort of thing that you mentioned.
yeah, okay.
Um,
I guess that would maybe it's at least like a good proxy. I don't know. Yeah.
yeah.
Does
Okay.
make sense.
But yeah, finishing covering this basically. So the idea is for the first pipeline, like I said, they decompose. Sorry, I'm skipping around slides here, but I kind of put these in a bad order. They decompose sorting the tokens by source rank, and then that way they can compute the sequence for group gem beginning with the local data while transfer of remote tokens proceeds concurrently. So that's what they're showing here is that when you prioritize the blue, the local data, these tiles all along this top chunk of this matrix can proceed immediately while the transfer of these that's needed for these other tiles proceeds. Headphone battery is running low. Oh well, it should last the presentation. Anyways, now for the second pipeline, which is the gem, the second group gem feeding into the top K reduce and alt all or reduce scatter. It's a little bit different. So the reason why we can do that prioritization of like local data, like arbitrary ranks or not ranks, rows in the that are local for the first one is because they were independent along M, right? These are all individual token vectors, and for the gem, there's no like inter-token dependency like there would be in something like attention, where like order matters, and we're doing like ops that cross token boundaries or across the M dimension. Here, these are independent just for a simple gem, right? So you could do them in whatever order as long as you don't, as long as the numerics of the output gem are consistent, right? So basically, it's not the case for the second stage of the pipeline because we're doing a top K reduction, which means that for these output gems, if you or not gems, like rows, if you think we go through the first gem and output activation, now we have like updated rows here, so to speak. Um, we need to do a top K reduction for each one, so we can't like reorder along the M dimension because we need to do a reduction and aggregate if we did like K equals 2, and so we have like the outputs from two experts, we need to aggregate those, reduce them, and so we can't just like arbitrarily reorder because it's convenient for our computation. Um, we are independent along the N dimension though, which is the feature dimension, because we'll go to the next slide here. Basically, we can, as long as those columns are available, then like along the N dimension again, then you can do your like as long as those columns are available for all three experts, you can proceed with your top K reduction because that feature dimension is independent, and so that's basically what they do is they restructure this gem. So this, okay, let me back up. This diagram is terrible in my opinion, and so let me explain it. The colors, surprisingly, and to my great confusion, do not correspond to the experts. Okay, the colors correspond to the order of execution. This is very confusing in my opinion because colors really have no inherent ordering to them, so it doesn't make for a very intuitive diagram. It seems more like a categorization, like we were saying, like zero belongs expert zero is like the yellow, and Anyways, what they're trying to say is that we do in the naive, or not naive, vanilla group gem, the execution order would be yellow, green, then blue, right? So we do expert zero, expert one, then expert two. The problem with this is that we cannot proceed with a top K reduction, right? So these tiles here, these are the outputs of each expert, right? We can't reduce along all three until all three experts compute. So basically until the entire gem is like done. Um, However, if we did something smarter and instead of doing the computation like expert wise or in expert order, we do it column wise. So we do compute one group of columns for all three experts in the yellow. Then we can concurrently proceed to the green and start computing that column while also proceeding with the top K reduction and then the all to all for those reduced tokens, right? And then we're overlapping. And that bubble is very small, right? So does that make sense for the column-wise computation of the group gem and why that is the way we're doing it? And to be clear, the TN here, that is the tile size of the group gem, so that we're still doing full tiles and getting reasonable, tensor core utilization and not, because what they say also in the paper is that you can't just do like weird levels of granularity, like for each, like for example, for each row that comes in, maybe like doing like kicking off the gem just for that row immediately. It just is like super inefficient just due to like hardware utilization reasons. It's like a super super skinny gem that's like not great, and also doing like I/O with that level of granularity is not good, like network transfer. So this is like the best of both worlds, where you have TN columns, you get full tiles for this computation, um, and then you also get because these need to be computed, right? We're doing group gems to compute these columns. We do the top K reduction and then start transferring L to all that column while we do start over the process and do the green one. Does that all make sense? Does that hopefully I explained clearly? Any comments or questions?
Just one question, like since the communication is asynchronous, we don't really know whether the same tiles are coming up, like are being received, right?
I don't know. Sorry, can you? I don't elaborate. I don't know what you mean.
So like we'll receive the data tile by tile and do the group gem tile wise instead of expert wise.
Close.
But
We'll do the computation tile by tile and do the computation column wise, but then then we do top K reduction and all to all, which is not tile wise. It will presumably do that whole chunk,
oh,
right?
okay.
Yeah, with comms kernels, they like a big contiguous chunk of data from what I've seen. It's like more efficient that way.
Interesting. And yeah, the colors are very confusing. Like I don't know what's happening there.
Yeah, yeah, yeah. Did it make sense after I explained that like it's the order of operations? Like we're doing beige, then green, then blue.
Yeah, it's
Okay,
the
okay.
order of operations and the output that sort of makes sense, but
hmm
I don't know why they have labeled it the experts with the same colors then.
Yeah, yeah. Because the experts, it's the order of operations here too. They do expert zero, then expert one, then expert two. But the labeling, like the they mix. Yeah, it's just a bad diagram. I should have made my own diagram for this, but that's part of the thing with I think is useful about reading like a reading group is versus doing it independently is because there's like parts of the paper that are hard to understand not even for like complexity reasons, but just for like it can be poorly written, or like a single sentence can like require like a bunch of background knowledge to understand, and they don't elaborate on it, and it's just useful to be able to like figure it out and then talk about it. So yeah,
Mhm.
all right.
Yeah.
um, last couple things here. So now, so that's the granularity mismatch in the more granular overlapping achieved that we just talked about via that decomposition and pipelining approach. Now, as far as the adaptive resource requirements, um, whoops, where'd it go? There we go. So what they do is, well, first they note there's a different way you could do this. You could do I don't even. They just put like one sentence on this. They said the vertical fusion, which is putting comms into the prologue or epilogue of a like compute kernel or vice versa. Um, it results in irregular overlap, so they didn't do that way. So it's like, okay, cool. And so what they do instead is something called thread block specialization, which is basically these logical groups of threads in your kernel will be specialized to do like a specific role in this computation pipeline, one for compute and one for comms. And the number of thread blocks that you dedicate in that kernel can be adjusted dynamically. These are compile time variables, though. Like I said earlier, um, basically I shouldn't say this is bad phrasing. Dynamically at runtime, they are pre-computed, or not pre-computed. They here. Let's skip to the next slide. So basically, they tried doing some experiments adjusting the number of comms versus compute thread blocks, right? And then they found that based on the input sequence length and the parallelism used, the optimal ratio of compute versus comms thread blocks is different. So what they did is just decide on some number of pre-computed kernels with these threshold variables that can be dispatched based on the input sequence size M and then the parallelism configuration. And so that part, the dispatch is dynamic, but the kernel computation and thread block ratio is known at compile time. It's just the dispatch, which one we dispatch is dynamic. Um, so yeah, and they also just mentioned that for the actual computation of the group gem, the compute thread blocks, they use warp. Something you can do on Hopper architectures with TMA, like async data transfer from global memory to shared memory and from shared memory back to global memory, to have like a producer warp responsible for moving data from global to shared memory, and then some kind of synchronization for the consumer warp to then consume it as soon as it's ready, and then write the data back asynchronously with TMA to global memory. And then the comms thread block will read that data from global memory and then do, like whatever the top K reduction and all to all. My question here, and I'm curious if anybody knows the answer to this or has their speculation, why is this extra write to global memory necessary? Because in Hopper, there's thread block clusters which allow warps on different, basically like your thread blocks on these different SMs here can communicate and synchronize with each other directly via shared memory without going through global memory, which is much higher latency and lower bandwidth. So I was curious if they're using these more advanced Hopper features for like warp specialization. Why don't they use thread block clusters to avoid this intermediate write? My only thought was maybe it has to do with just the shared buffer that we talked about and the pipelines that are needed is just not big enough. Like when shared memory, like it's just a much smaller space, and so maybe it's just you need to use global memory. I don't know. Does anybody else have any thoughts on like why this would be necessary to go back and forth to global memory? Okay, well, I'll assume my speculation is correct then, or at least, and maybe in the GPU mode Discord or something, there's some kernel experts who can give their speculation. Yeah, this is the kind of stuff that I wish maybe they said it in the paper and I just missed it, but I kind of wish they, kind of gave more details on that. Um, but yeah, we already kind of discussed this slide, so I'll skip past it, and then I guess not even skip. Like I already covered this slide, so we'll move on. Finally, the results. This is the end. It just shows a ridiculous speed up. So this is the average end-to-end speed up for tested models. It was 1.71. And then the MOE layer specifically when tested was 1.96 speed up, which is really impressive speed up. Um, for I mean that's kind of an artifact of because I was gonna say like I've done kernel optimization work where I do a ton of work and I get like a 2.5% speed up and it's like a hard fought speed up, and this is like a ridiculous speed up. But that has to do more with the fact I think that what we are optimizing, like the 47% exposed comms, there's a lot of room for improvement there. So I think like there's you know if you do some clever overlapping and more efficient pipelining like this, you can achieve a really good speed up. So yeah, I was really interested in this paper. I think it's going to be interesting to kind of try to integrate these ideas into ML frameworks natively rather than just be and just make it more accessible to people. So rather than to just be these you know basically kernels you can use in their repo. Which by the way I have open. It's just like not easy to understand. Like one of my questions is, um, like how do they ensure that they're like I looked through this and I saw they had something called like a tile scheduler in Cutlass, which I've used Triton a lot. I've used CUDA some. I've not used Cutlass very much. I've done like one Cutlass kernel. I didn't do like really meaningful changes on it. But my just like looking at the actual, and this is the other annoying thing, they release it all in just one giant PR without any details on the implementation. So you can't even like blame the code and then get the context for like what this is doing. But anyways, my point is, they had something called a tile scheduler, and I think that's probably how they implement the what we were talking. Oh God, where's the slides? Talking about here with the rescheduling of the tile computation to prioritize these local tokens first. Um, I assume so because I was kind of wondering if I could re-implement this in Triton with symmetric memory, especially if we get support for internode comms and NVSHMEM for the kind of more granular compute primitive or not compute comms primitives than just like all gather. You can just do like put and set and things like that. But it seems like the answer is no because there's no way I know of in Triton to manually like define your own tile scheduler. I think the compiler handles that. Um, so I am kind of depressed. I don't know. Does anybody know um, more details about Cutlass and how you might implement something like we talked about today? There you go, tile scheduler. Yes.
Isn't tile like a first level primitive in Cutlass? Like you don't go below tile level, right? And I'm
Um,
guessing there will be.
I think so, but I'm not familiar enough to say that with confidence. But like yeah, here, see they have tile scheduler. So they use underlying schedule, persistent tile scheduler for SM90. Okay, let's just like kind of read through this and see raster order options, number of nodes, rank world. So this is multi-node. World size, local rank. Okay, world index layout, shape, stride, sets. See, is cluster shape, is that the thread block. Maybe they are using thread block cluster. Like, is that what that's referring to?
Fluffy says that Gluon will give you more control, like Gluon compiler.
What did you say? Sorry.
There's a message in chat for an answer to your question about having more control over the tile scheduling.
Oh,
There's apparently a Gluon compiler which will give you that.
oh, I just heard. Isn't this like the new OpenAI thing?
Long time.
A lower level language based on some exposed controller memory layout scheduling. Oh, cool. So,
And what it really is, it's
yeah, isn't this also? I also heard they're not like it's not like for the open source community or something. It's like they're not. Let me see. Trying glue on. There's also something on PyTorch called Helion. Is this it? Experimental glue on. So is this actually usable? Like, could I? Is there? So they mentioned the tutorial. Gluon.jit. Wow. See, my also question was like these abstractions, especially Cutlass. Like, I just get frustrated trying to read this. Like, I mean, I should just buckle down and like really get in the weeds with this, but I feel like abstractions for this type of programming that's like super like chip architecture aware and low level, I hate the abstractions. Feel like they get in the way to me, and I like that's why I like just CUDA because I can like just directly see what's happening and control it. And so that's why one of my questions was, um, anything's usable if I'm brave enough. True, that's accurate. Yeah, so but if I was just using like how hard would it be to implement custom tile scheduling just using CUDA? Because something like a group gem and then using like NVSHMEM, I could picture doing directly in CUDA, and that seems doable for the like more granular comms and then compute like this like interleaving of the two. But the tile scheduling is something that I am not clear on like how that would even be implemented. But I assume it must be
Yeah.
possible in CUDA.
Also, like,
Hmm.
also, like, how would you know when you have some data?
There's
You'd have to have some sort of like signal or
yeah,
like some like semaphore
yeah,
for
exactly.
the, like per tile, which is crazy.
M barriers and memory fences. So that's like what you're describing basically, like synchronization primitives, where you have like yeah these
Yeah,
atomics, um,
which is
and
weird because what is this? Is this all one? So it's the communication and the compute happens on one kernel, like one CUDA
yeah,
stream.
it's one kernel just do different thread block specialization.
I see.
Yeah,
So that does make more sense that it would be possible.
yeah, and then they have is this memory fence. I think this makes sure that it can be enforce sequentially consistent ordering on memory accesses.